lasers. We see them everywhere, from sci-fi movies to the barcode scanner at the grocery store. But have you ever really stopped to think about what a laser beam is? Because it's not just a really fancy flashlight. Nope. It's light that has been totally tamed, perfectly organized, and amplified on a quantum level. And in this explainer, we're going to pull back the curtain and see exactly how it all works. Okay, so to get this, think about a normal light bulb. It's like a big, chaotic crowd of people all shouting at once. The light just spreads out randomly in every direction. But a laser is like a perfectly disciplined army. Every single particle of light, every photon, is marching in perfect formation. They've all got the same direction, the exact same wavelength, and they're all perfectly in step. This amazing property is what we call coherence. So the big question is, how do you get from the total chaos of a light bulb to the perfect, beautiful order of a laser beam? Well, the answer actually takes us way back to 1917, and a name you probably recognize, Albert Einstein. Yeah, it all kicked off with one of his famous thought experiments. Einstein figured out that for all the laws of physics to make sense, there had to be this third, undiscovered way for light and matter to interact. And this missing piece of the puzzle, it would turn out to be the secret ingredient for every laser ever made. It really just boils down to three basic ways that light and atoms can play together. First, you've got absorption. An atom literally eats a photon and jumps up to a higher energy level. Simple enough. Second, spontaneous emission. That excited atom gets tired, randomly falls back down, and spits out a photon in any old direction. That's basically what's happening in a light bulb. But this third one, stimulated emission, now that's the magic. So here's the trick. With stimulated emission, if a photon with just the right amount of energy comes along and hits an atom that's already excited, it doesn't get absorbed. Instead, it stimulates that atom to release a second photon. And this new photon is a perfect, identical twin of the first one. It's basically a quantum copy machine. And this is the A and the SE in laser, light amplification by stimulated emission of radiation. Okay, so we've got a way to make photon clones. That's awesome. Problem solved, right? Well, not quite. There's a pretty big catch. See, by default, nature is actively working against us. In any normal material, atoms are kind of lazy. There are way, way more of them just chilling in their low-energy ground state than are buzzing around in an excited state. And what that means is an incoming photon is far more likely to get eaten, absorbed, than it is to create a clone through stimulated emission. So instead of amplifying light, you just end up dimming it. Not what we want. So to get around this, we have to cheat. We have to force the material into this totally bizarre, unnatural state called a population inversion. We do this by pumping a ton of energy into it, forcing more atoms into that high-energy excited state than the low-energy one. It's only when we flip the odds like this that our cloning process even has a chance to win. Now, the very first lasers used a brute force approach called a three-level system. You pump atoms all the way up from the ground state, and they create laser light by falling all the way back down. This takes a huge amount of energy. The real breakthrough was the four-level system. Here, the atoms only have to fall to an intermediate level that's almost always empty, which makes creating that population inversion way, way easier. And that's why four-level lasers are just vastly more efficient. All right, so now we have our super energized material. It's primed and ready to amplify light. But one photon creating just one clone, that's not going to cut it. We need a massive chain reaction to get an intense beam. And to do that, we need to build an echo chamber for light. Right, we want one photon to become two, two to become four, four to become eight, and so on. To make that happen, we've got to trap the photons inside our energized material so they can keep making more and more clones. The solution is actually pretty simple, an optical resonator. It's basically just two mirrors placed at either end of our laser material. And here's how it goes down. Some random photon kicks the whole thing off, creating a clone. Now there are two. They zip to the end and hit a mirror, which bounces them right back through the material. On this second pass, those two photons create two more. Now we've got four. Those four hit the other mirror, turn around, and create four more. You see where this is going. This incredible avalanche of photons bouncing back and forth is what builds up the crazy intensity of a laser beam. But wait, there's more. That resonator does another crucial job. It acts like a filter. Think of a guitar string. It could only vibrate at specific notes, right? Well, this optical cavity will only support light waves that fit perfectly between the mirrors, creating what's called a standing wave. This is what forces the laser light to be so incredibly pure in its color, or monochromatic. Any other wavelengths just cancel themselves out and disappear. So, we're pumping energy in, that photon avalanche is starting to build, but here's the thing. Light is always being lost. It's leaking out, getting scattered or absorbed. So there's this constant battle happening inside the laser between gain and loss, and it all comes down to one critical tipping point. This is what we call the lasing threshold. It's that exact moment, that break-even point, where the amplification, all that gain from our stimulated emission, is finally strong enough to overcome all the losses. The moment the gain equals the loss, you've hit the threshold. And as soon as you push past that threshold, everything changes. It's like flipping a switch. Stimulated emission completely takes over. The output power, which was almost nothing before, just skyrockets. And what comes out is that intense, pure, coherent beam we've been working towards. The laser is officially lasing. It's on.
So we did it. We have an intense, pure beam of light. But for it to actually be useful for something like surgery or communications, it needs one last thing. It needs to have a really high-quality shape. And guess what? That same optical resonator, our two trusty mirrors, has one more trick up its sleeve. The specific geometry of those mirrors doesn't just pick the wavelength. It also carves out the beam's cross-sectional shape and intensity pattern.
These patterns have a name, transverse electromagnetic modes, or just TEM modes. And while you can make all sorts of complex shapes, like donuts, the holy grail for most jobs is the TEM00 mode. It's a perfect Gaussian profile, a single, clean, bright spot that you can focus down to the tightest possible point. This is the perfect beam that makes precision possible.
And there you have it. We went from a quantum hunch that Einstein had over a century ago to forcing atoms into a totally unnatural state to building an echo chamber for photons. And in the end, we learned how to tame light itself. We turned a fundamental principle of the universe into a tool that has completely reshaped our world. And it all started with just one simple idea: making one photon a perfect clone of another. Really makes you wonder, doesn't it? What will we build with it next?